Good morning. This is our very last lecture for the semester. We're going to continue our discussion of analysis of categorical data. Today we're going to talk about the two-way chi-square. And again, this is in chapter 11. Another name for the two-way chi-square is the test of independence. This particular hypothesis test determines whether two categorical variables are independent of each other. It determines whether two categorical variables are independent of each other. A test of independence. So in this particular analysis, we're looking for relationships. Analysis is all about relationships. Independence or dependence. We know dependence implies there is a relationship. Independence implies there is no relationship. So in terms of a null hypothesis and an alternative hypothesis, the null hypothesis implies independence. And independence is all about no relationship. So if we accept the null in the two-way chi-square, we're concluding that there's no relationship between category 1 and 2. They're independent of each other. The alternative hypothesis implies dependence. And we know the term dependence implies there is a relationship. When two entities are in a relationship, they're dependent on each other, right? So dependence, there is a relationship. We can set alpha at 0.05. Again, we know that before we run any statistical test, p equals alpha. Is category 1 independent of category 2, or is it dependent? Let's see. With an example. Back in 2008, we surveyed 200 individuals. And I want you to remember back in 2008, if you remember, in about September of 2008, it was right before the 2008 election. And yeah, the results of the 2008 election were, that the Democrat won, Obama won, okay? But I want you to think back, okay? In about September of 2008, in terms of being a young person, back in 2008, would you say that the majority of young people would claim that they were Democrat or Republican? Right, Democrat. Yeah, Democrat. Well, let's test your hypothesis, okay? The question becomes, is political party dependent on age, or is it independent of age? Okay, we all think that the young people, the majority of young people were Democrat. Okay, back claimed to be Democrat back then. But we have two variables. We have political party and age. And we have Democrats, Republicans, and independents, the individuals that are kind of on the fence. This example is actually out of political science. Age groups, we have the 18 to 34-year-olds, the 35 to 51-year-old age group, and 52 to 68. And And as it turns out, class, in terms of these 200 individuals, and let's assume that these 200 individuals were randomly selected from the population. So we have a representative sample of individuals here. Each member of the population had an equal likelihood of being selected. As it turns out, 50 young people, 50 individuals in this particular age group said that they were Democrat. 10 said that they were Republican. 15 independent. The independents are kind of, on the fence. They ultimately went to the Democratic side. In the 35 to 51-year-old age group, 15 individuals told me they were Democrat, 25 Republican, and 15 independent. In the 52 to 68 age group, 25 said they were Democrat, 35 Republican, and 10 independent. Is political party preference dependent on age? I don't know. We have this two-way chi-square that helps us answer that question. We have a null hypothesis that states that there's no relationship between categories. An alternative hypothesis that says that there is a relationship. We'll set alpha at 0.5, and we know that before we run any statistical test, p equals alpha. Degrees of freedom in this two-way chi-square is the number of rows minus 1, the number of rows minus 1, times the number of columns minus 1. The number of rows minus 1 times the number of columns minus 1. Well, we have 3 rows, right? Minus 1 is 2. 3 columns minus 1 is 2. 2 times 2 is 4. We have 4 degrees of freedom, 0.5 alpha. We can find a critical value on page C23 of our textbooks. We go across the top to 0.5 and down the side to 4. And there's a number there. What is that number?
9.488.
9.488. If chi-square exceeds this, we have enough evidence to reject the null. And again, this is telling us that this particular chi-square sampling distribution at 4 degrees of freedom, because p is 0.5, about 5% of the area under this chi-square sampling distribution falls to the right of this number, and about 95% falls to the left. We have our data here, and what we actually have are 9 observed frequencies. So we have 9 observed frequencies, and so I'm going to put a little equals O after each one of these numbers. And that just means that this is an observed frequency, and we have 9 of them. And I'm just going to do this. And we have 200 total subjects. Now, if you look at chapter 11, lots of examples of this, but it will tell you that there's a special way that we determine expected frequencies in this two-way chi-square. And watch very closely. We have to do this 9 times. First, we create what we call marginals. We add across this plus this plus this, 75, 55, and 70. We just add across. And then we add down. This plus this, 90. This plus this, 70. And 40. And if we add these numbers, we get 200. If we add these numbers, we get 200. Special way of determining expected frequencies. Watch very carefully. And we'll start with this cell right here. Expected frequencies. We go over to this margin, 75, and then down to this margin, 90, multiply those two numbers together and divide by the total. So we go over to the margin, 75 times 90 divided by 200 gives us an expected frequency of 33.75. For this cell, we say 75 times 70 divided by 200 gives us an expected frequency of 26.25. For this cell, we say 75 times 40 divided by 200 gives us an E of 15. For this cell, 55 times 90 divided by 200 gives us an expected frequency of 24.75. For this cell, 55 times 70 divided by 200 gives us an E of 19.25. For this cell, 55 times 40 divided by 200 gives us an E of 11. For this cell, 70 times 90 divided by 200 gives us an expected frequency of 31.5. For this cell, 70 times 70 divided by 200 gives us an E of 24.5. And finally, for this cell, 70 times 40 divided by 200 gives us an expected frequency of 14. So we have 9 sets of O's and E's. We have 9 sets of O's and E's. Now we could do a sum O minus E squared over E 9 times, but the book suggests that we just set up this little chart where we have O, E, O minus E, O minus E squared, and O minus E squared over E. We just set up this little chart, O, E, O minus E squared, O minus E squared over E. And we list all the O's and E's, making sure that the E's correspond with their respective O's. So we list all the O's and E's. And the E's. We list all the O's and E's, make sure that the E's correspond to their respective O's. And then we do what this thing tells us to do. O minus E, 50 minus 33.75 is 16.25. 15 minus 24.75 is negative 9.75. Negative 6.5. Negative 16.25. 5.75. 10.5, 0, 4, negative 4. O minus E. We then keep the thing going and just take each O minus E data point and square it per these instructions. 16.25 squared, 264.1. Negative 9.75 squared, 95.1. 42.25. 264.1. 33.1. 10.5 squared, 110.25. 0, 16, 16. O minus E squared. Then we take each O minus E squared data point and divide it by its respective E. So we say 264.1 divided by 33.75 is 7.83. 95.1 divided by 24.75, 3.84. 1.34. 10.06. 1.72. 4.5. 0. 1.45. 1.14. O minus E squared over E. And the chi-square is just the sum of this column. We know the chi-square is sum O minus E squared over E. If we add all these numbers up, we get 31.88. The chi-square is 31.88. And we have a decision to make, right? We compare the calculated statistic to the critical value. We see it exceeds it. Therefore, our decision obviously is to reject the null. What happened to the p region? Yeah, it got smaller. If p is less than alpha, we reject the null. The needle actually shifted from the critical value of 9.488 out to 31.88 and made that region of p smaller than 5% of the area under the chi-square sampling distribution. We now have enough statistical evidence to answer the question. Class, is political party dependent on age or is it independent? It's dependent, yeah. There's something going on here. So when you said, you know, yeah, I believe in 2008 the majority of young people voted Democratic, you were correct. We actually confirmed your hypothesis. Political party is, you know, in this particular case, dependent on age. We know how the 2008 election turned out as well. Now again, you know, there's a small likelihood that my decision to reject this null was not a correct one. So I rejected with some pretty high certainty. And the probability I committed a type 2 error is a non-entity. The two-way chi-square, and you see this a lot in the literature. Most of the chi-squares that you see run out there, and the problem is that when you're reading some journal, you know, when you're reading the Journal of Agricultural Science or whatever, they'll tell you that the results of the chi-square test of independence is, most people don't know what a test of independence is, okay? You do. It's like this special, it's like, you know, like guy code and girl code. Well, it's like science code, you know, and you're supposed to know what that means. So, the two-way chi-square. Okay, let's do this again. Class, I got a question for you. Do you approve of the war? You know, the stuff going on in Iraq and Afghanistan and stuff like that. Do you actually approve of that? Okay, let me rephrase that then. We have a real responsive class this morning. In terms of the war, let's think about gender differences. The differences between men and women. That's always fun to kind of discuss, you know. Men are from Venus. No. Yeah, men are from Mars, women are from Venus, you know. Gender differences. In terms of like approval rates for the war, do you think women would like more approve of the war or disapprove of the war? Disapprove. You know, I would agree with that. I would agree with that, yeah. Well, it turns out we surveyed 214 individuals. And we asked the question, you know, do you approve of the war? Do you approve of the war? Well, as it turns out, you know, we got two categories. I'm going to put the gender category up here. It doesn't matter where you put the category. You know, we got men and women. And we have, you know, approve, disapprove. Well, as it turns out, 49 men told me that they approve of the war. 62 women indicated that they approve of the war. That's interesting. You wouldn't think that, would you? But we have to remember what kind of sample. If we see these kind of results, what kind of sample might this be? Yeah, maybe a bias sample. You know, these may be army wives, you know, or something like that. You know, is that show still on? Lifetime channel. Okay.
Or if there was more like women sampled too.
Yeah, yeah. 55 men disapproved of the war. 48 women disapproved of the war. You know, is approval rate dependent on gender or is it independent? You know, do a significant amount of women approve of the war, or is what I'm seeing here just a result of chance? Yeah, I don't know. Let's get this thing set up. We're going to keep alpha at 0.5, and we know P is 0.5. Degrees of freedom, the number of rows minus 1. We have 2 rows minus 1 is 1. 2 columns minus 1. 1 times 1 is 1. 1 degree of freedom, 0.5 alpha. We go to the table. Across the top to 0.5, down the side to 1. There's a number there. What is it?
3.841.
3.841. If chi-square exceeds this, we have enough evidence to reject the null. We have 4 observed frequencies here, so I'm just going to put a little equals O after each one of these. And just draw a little box. We have 214 subjects. And we said we have a special way of determining expected frequencies in this two-way chi-square. We have to set up our margins, our marginals. This plus this, 111. This plus this, 103. Add these numbers together, we get 214. This plus this, 104. This plus this, 110. Add these numbers, we get 214. Let's compute our expected frequencies. We'll do this exercise again. This time we only have to do it 4 times. We have 4 cells. We'll start right here. 111 times 104 divided by 214 gives us an expected frequency of 53.94. For this cell, 111 times 110 divided by 214 gives us an expected frequency of 57.1. For this cell, 103 times 104 divided by 214 gives us an E of 50.06. For this cell, 103 times 110 divided by 214 gives us an expected frequency of 52.94. So we have 4 sets of O's and E's. Now, we could do sum O minus E squared over E 4 times, right? Let's set this little chart up where we have O, E, O minus E, O minus E squared, and O minus E squared over E. We list the O's and E's, making sure that the E corresponds to its respective O. List the O's and E's, bless you. And then follow our nose, do what this thing tells us to do. O minus E. This minus this, negative 4.94. This minus this, 4.9. This minus this, 4.94. This minus this, negative 4.94. O minus E squared, negative 4.94 squared, 24.4. 4.9 squared, 24.01. 24.4. 24.4. Gee, we see a lot of equal numbers here, don't we? Equal. What might... let's see how the result is. O minus E squared over E. This divided by this, 0.452. This divided by this, 0.420. This divided by this, 0.487. This divided by this, 0.461. The chi-square we know is sum O minus E squared over E. And if we sum this column, we get 1.82. Chi-square is 1.82. We have a decision. This is our very last one of the semester. Yay. We compare the calculated statistic to the critical value. We see it doesn't exceed it. Therefore, our decision is to accept the null and accept this statement of independence. No relationship. Class, is approval rate dependent on gender? No. No, it appears to be independent. What we're seeing here probably just happened by chance. Now, in this particular case, we know that alpha is kind of a non-issue. There's a small chance I may have made a type 2 error. The two-way chi-square. Okay. Let's talk about this exam that's coming up on Tuesday morning. This exam will be a final examination on inferential statistics with a focus on this last section. So there will be a lot of questions on ANOVA, a little bit on chi-square, but mostly on ANOVA. But since this is a final examination, I'm going to expect you to remember a lot of that basic stuff. Okay. Like the other exams, about 15% of this exam will be computational. So you're going to compute a one-way ANOVA and a two-way chi-square. We did plenty of examples of one-way ANOVAs, and you're going to compute one of these two-way chi-squares. But those questions will only constitute about 15% of the exam, all right? The remaining 85% of the questions will be conceptual in nature. What do I mean? Well, lots of questions on ANOVA. I actually have a copy of the exam right here. You know, lots of questions on the F statistic. You know, what is that F statistic? It's a ratio between groups variation divided by, you know, within groups variation. You know, questions on the little pieces of the one-way ANOVA. You know, we talked about a lot. We talked about the omnibus F, you know, that computation of the overall F. When we're computing F, we are partitioning sources of variation in the form of sums of squares into, you know, between, within, and total. But, you know, just looking at the exam here, there's questions on other sections as well. You know, for instance, you know, you're still going to have to know what point estimation is, what a confidence interval is, you know, and all those little basics from that first lecture. You know, I might ask you a question on, you know, what a p-value is, or what a one-tailed hypothesis is, you know. There's going to be lots of situations where you're going to have to do the rule, both the, you know, the critical value approach and then the p-value approach. So there are going to be little exercises where you make decisions, okay? Central limit theorem, sampling distributions, be questions on those, you know. So be prepared, just like you were last time, to, you know, this is another exam on inferential stat. So the focus will be on ANOVA with a little bit of chi-square, but you're still going to have to know when to use, you know, appropriate statistical tests. I might throw in a question on the z-test. You never know. I might throw a question in on the one sample t, just for good measure. Yes?
Post hoc?
Yes. Whenever we reject the null in any ANOVA, what's the next step?
Post hoc.
Post hoc. Know those familiar post hocs for the one-way ANOVA. What are they? Tukey, Chaffee, Dunne, Bonferroni. Okay. There'll be some questions on the advanced ANOVAs. They won't be difficult questions. They'll be very simple general questions. I want you to be able to, you know when to use a multivariate analysis of variance, a repeated measures analysis of variance, you know, a two-way ANOVA, you know, that factorial ANOVA, and the analysis of covariance. Know what a covariate is, you know, all the little pieces, and it's everything that I, you know, presented, you know, in that one lecture. They're just all the basics, advanced ANOVA basics. The assumptions for the one-way ANOVA are the same as they are for the two independent sample t-test. So the assumptions for the one-way ANOVA are the same as the assumptions for the two independent sample t-test. And what are they? Normality, randomness, homogeneity of variance, also called homoscedasticity, and what's the fourth one? Right, independent observations. So remember that the assumptions for the one-way ANOVA are the same assumptions that we use for the two independent sample t-test. And remember, you know, the one-way ANOVA is just an extension of the two independent sample t-test. There's going to be some questions on type 1 and type 2 error. Let's just do a little bit of reviewing. I want to make a little point clear. When I discussed alpha, and also when I discussed power, you know, I said that, you know, as alpha increases, power increases. And so, you know, as these numbers go in this direction, they get larger. So the likelihood of committing a type 1 error here is higher than the likelihood of committing a type 1 error here or here. This is considered, pretty conservative. But I could also do this and tell you that the relationship between type 1 error and type 2 error is inverse. What do I mean by that? Well, if I make alpha too conservative, it increases the likelihood that I commit a type 2 error. Why? Because if I make alpha too conservative, if the likelihood of a type 1 error is too low, then the critical values are high. It takes a higher test statistic to reject, and I might be missing something. So the relationship between alpha and beta is inverse. As the likelihood of a type 1 error increases, the likelihood of a type 2 error decreases. It's less likely to commit a type 2 error up here because the critical values are lower, and there's a higher likelihood of rejecting the null. As beta decreases, alpha increases. Type 1 and type 2 error. It's an inverse relationship. There'll be questions on chi-square. You'll not only compute a two-way chi-square, but you will answer all kinds of questions on the one-way chi-square, that goodness of fit test, the two-way chi-square, the test of independence. Your exam will consist of 71 questions. It shouldn't take you more than an hour and a half or so to finish. There's never been a problem with finishing the exam on time and stuff. Yes?
So we're not computing a one-way?
Right. So you'll compute a two-way chi-square and a one-way ANOVA. Yep. I'll have a formula sheet for you. I also have a really good final exam review sheet that I'm going to be emailing you on Angel. It will be in your inboxes. This is a review sheet that was actually compiled by a former student who was drafted by the Kansas City Royals some years ago, and he had me for stat, and he put a lot of work into getting a good grade, and one of which was putting this review sheet. And it was so good, he showed it to me, it was so good that I asked him if I could use it in future classes. And he said, yeah. So anyway, if they're not, is there any questions? All right. Yes, quick one. Yeah.
Well,
Okay, that concludes lecture number 20. I will see you next time.